Hello, everyone. So we are talking about these fundamental topics on Unit 9. Make sure you're taking notes, following along. It's not difficult at all, but it is foundational. So make sure you're paying close attention, and make sure you are writing notes as we go. I'll be checking these off in class. Okay, page 10. Page 10. Okay. We discussed last class what thermodynamically favorable means. A thermodynamically favorable reaction is a reaction that happens if the reaction happens, it was thermodynamically favorable. And so Gibbs free energy, again, we described a little bit last class. I'm going to go into a lot more detail right now. But Gibbs free energy is our way of determining in chemistry if a reaction is thermodynamically favorable. Will it occur in certain environments at certain temperatures? And so how we analyze this is with Gibbs free energy. Okay. Now, Gibbs free energy relies on us being able to analyze enthalpy and entropy. Okay, enthalpy, entropy. So first off, just a reminder about this. Our enthalpy is a change in energy. Okay, a change in energy. And if our delta H value, if it is negative, then that means it was an exothermic reaction. Heat was released. It was lost by the system, released to the surroundings. Exothermic. If we have a delta H that's positive, then it's endothermic. Okay. Now, I will say endothermic reactions absolutely happen, but exothermic reactions are favored. That naturally, due to this reaction, I'll show you, due to the formula for Gibbs free energy that I'll show you in a moment, that it is easier for a reaction to happen when it's exothermic. Okay, so more likely to occur. What's another way of saying that? It is more likely to be thermodynamically favorable, right? If it occurs, it was thermodynamically favorable. Now, on to entropy. Entropy, we talked about it today, and it was our measure of chaos, right? So delta S would be a change in that chaos. Order. Did it increase in order? Did it decrease in order? And that's our entropy. We've talked about this, that when our delta S is negative, it became more orderly or less chaotic. More ordered. And that if it's a delta S that's positive, then it became more chaotic or less ordered. The less ordered nature tends towards entropy, towards disorder, is more likely to occur. Okay. It is more like, if a reaction has a positive change in entropy, it is more likely to occur or more likely to be thermodynamically favorable. That doesn't mean that there aren't reactions out there that are negative for their entropy, that can still happen. It does, but not always. This one is way more likely to happen. We're going to discuss why. Okay, here's the equation for Gibbs free energy. This is on your blue reference. You're not, I can't remember. Actually, we are going to do a few small calculations. It's easy enough. But I need you to know that when delta G, so let's put it up here, when Gibbs free energy, when delta G is positive, this is not thermodynamically favorable. It doesn't happen. But when delta G is negative, then it was thermodynamically favorable. Then the reaction does happen. Okay. Our delta H, not always, but usually in kilojoules, and it's important that we pay really close attention to the units. Temperature needs to be in Kelvin, and then delta S is kilojoules per Kelvin. Because we multiply those together, Kelvin cancels, and we're left with kilojoules. If these energy units are not the same, we need to convert them so they are the same. Now, we know that our goal here is, at least for a reaction, is for this to be negative. So let's think about that for a minute. The goal is for this to be negative. If delta H is a positive value, do you see how it fights against this? It's harder for delta G to be negative when delta H is positive. But it's easier for delta G to be negative when delta H is negative. Now the opposite is true for delta S because we are minusing temperature times by delta S. So if delta S is a positive number, we're going to minus that positive number, and that makes it easier for delta G to be negative. But if delta S is negative, then we minus that negative, and that skews delta G towards the positive. It's harder for delta G to be negative when delta S is negative. And that's the idea down here. Okay? So let's add these items in. So we're going to talk about the sign of delta H. We're going to talk about the sign of delta S. And then we are going to say, we're going to recognize if it's thermodynamically favorable and if there's a constraint on temperature. Okay, so we're going to analyze delta G. Is it thermodynamically favorable, and at what temperatures? And at what temperatures that's happening. Okay, so let's go with the one that we've talked about. We know that it's easier for delta G to be negative when delta H is negative. And we know that it's easier for delta G to be negative or thermodynamically favorable when delta S is positive. So when we look at a reaction, if it is exothermic and it increases in chaos or becomes less orderly, then delta G will always be negative. Okay? Delta G will always be negative. Let's do this. Delta G be negative. And so that means that it's going to be thermodynamically favorable at all temperatures. It doesn't matter if it's a low temperature or a high temperature. It doesn't matter if this impact of temperature is small or big. No matter what, we will always end up with a negative delta G. Now, if we do the exact opposite of that, if it's endothermic and we become more orderly, then delta G is always positive. And so it's not thermodynamically favorable. Like at no temperature, whether high or low, we do not get, it's not thermodynamically favorable. It will not happen. Okay, let's do, it is not thermodynamically favorable at all temperatures. Okay, all temps. Now, what if they're both positive? Now let's think about this for a minute. So if this is positive, then it's fighting delta G. It's trying to make delta G more positive. And if this is positive, it's trying to make delta G more negative. So now we have a race against each other. Which one's going to have the bigger impact? Will this skew delta G to the positive, or will this skew it to the negative? And so now we can see how it does become temperature dependent. That if temperature is small, then delta S isn't likely not going to win this battle between the two. But if delta T is a big value, then it multiplies the impact of delta S, making it way more likely that delta G will be negative. Now, if you don't see this in the reaction, like if you looking at this equation doesn't help you recognize this, that is okay. But then this is what I want you to remember. When delta H is positive and delta S is positive, the delta G has the potential of being either positive or negative, and it will be positive. It will be thermodynamically favorable at high temperatures. Okay, we only get that negative G, thermodynamically favorable, just do a little arrow to help us, if the temperature is high, because then this impact that's driving the reaction for delta G to be negative is bigger than that impact is. So positive, positive, well, only high temperatures then. Negative, negative, only low temperatures. Delta G has the potential of being either positive or negative, and again, it means this impact. This is pushing delta G to be negative. Now this is pushing delta G to be positive. And so we need this impact to be bigger than that one. If temperature is small, it lessens the delta S impact, making the delta H way more likely to drive this delta G into being negative. So that's why when this is negative and delta S is negative, then we only get thermodynamically favorable reactions at the low temperatures. So thermodynamically favorable, this negative delta G only happens at low temperatures. There are so many practice problems about this, like so many. And that's going to be a good chunk of what we're looking at and practicing next time. So let's look at this really quick. Before we even run any numbers, let's guess what might be happening here. So I have a delta H, it's exothermic, it's negative, and I have a delta S that's negative. So we got a negative and a negative. Oh, so delta G could be positive or it could be negative. It's going to depend on the temperature. The units for energy are not the same, so we definitely need to change that. How about we do delta H, we could change it to joules, so this would be 218,000 joules, because this one's already in joules. So then our delta S is going to be negative 765 joules per Kelvin. Oh, our temperature is in Celsius, and we need it to be the same. We need it to be in Kelvin. So take your 32 degrees Celsius and add 273.15 to make it Kelvin. And we are getting 305.15. Now, is this temperature high? Is it low? This is where it's hard to tell. There's not a line in the sand. I can't say if it's above this temperature, then it works, and if it's below this one, then it doesn't, vice versa. Unfortunately, it's really dependent on the reaction itself, so let's plug it into our equation and see. So we have delta G is equal to delta H minus temperature times by delta S. So we're going to take our value for delta H, and we're going to minus it from the temperature times by our delta S value. So without significant figures, I have 15,439.75 joules. Okay. If we want to, we can convert it to kilojoules. That would be 15 kilojoules. But what do we got sig fig wise? Yeah, that one was multiplied. So, right here. So actually, let's go with the kilojoules on the joule value, 3 sig figs. 15.4 kilojoules. And it was a positive number, so not thermodynamically favorable, because we had a positive. Did I get it? Yeah. Okay, good. At what temperature does the previous reaction become thermodynamically favorable? Assume that delta H and delta S do not change as the temperature changes. Okay, we're gonna do this. We're gonna change this up just a little bit because I didn't see an example question that was similar to that. But I want you to tell me, what do I need to do? Do I need to increase the temperature or decrease the temperature to make it thermodynamically favorable? So it's a negative delta H and it's a negative delta S. Oh, so it's only thermodynamically favorable at low temperatures. So we would need to decrease the temp to make it thermodynamically favorable. So we would need to decrease the temperature to make the reaction thermodynamically favorable. Okay, nice. Almost done. What do we think about this guy? So we have a negative for our delta H and a positive for our delta S. Is the process thermodynamically favorable? We could plug this in, right? We could do delta G is equal to delta H plus, minus T times by delta S, but do we need to? When delta H is negative and delta S is positive, then delta G will always be negative. It will always be thermodynamically favorable. So we don't need to do the math. We can automatically say that this reaction is thermodynamically favorable. And then you could explain why, and you could explain that any reaction that has a negative delta H, so any reaction that has a negative delta H and a positive delta S will have a negative delta G at any temperature. Okay. Last concept. Oh, so we're going to have a short video. That would be nice. What about reactions with really high activation energy? So this is the last concept. There weren't too many questions, but there were a few. And the idea was, what if a reaction is determined to be thermodynamically favorable? That it does in fact have a negative delta G, and then we go to do the reaction and it doesn't happen. And we say, well, why is that? And what we have found that the absolutely main reason why this might be the case is because the reactions have like unusually high activation energies. So as far as AP chemistry questions go, they had to be really clear. They had to tell you that the reaction is thermodynamically favorable, or it has a negative delta G. And then they have to say, but it still doesn't happen. And then you explain, almost always it's you explain, well, why might that be? And the answer is that the reaction, the RxN, the reaction has a high activation energy. So we'll do some practice problems in class, and we'll look at it and be like, hey, this is thermodynamically favorable, but for some reason it still didn't happen. And then that's the reason why. This is rare, not impossible, but rare. So just keep that in mind. All right, everyone. Thank you for your hard work, and I'll see you in class.